So last time we were talking about this business with fields and the fields sort of generated by a set. So if F and here it starts, then notation is subfield of F generated by X is the intersection of all subfields of F such that X is a subset of it. Right. So for example, if you have a field and X is the empty set, then this would be the intersection of all subfields, period. Right. So in characteristic 2 would be the rational numbers, and in characteristic P would be isomorphic to Z by P. If let's say X A1 N and K is a subfield of F, then first A1. So you should sort of take this sort of from the polynomial notation. This is the set of all okay. So what this notation means is take all so you've got a set of n things, right? Take all polynomials and n variables, right? And by the way, some of those variables to be omitted. Any possible polynomial and n variables, and plug these elements in order, right? So for example, notice that you contain the field K just by taking the polynomial to be the constant K, right? Whatever constant you want here. Notice that this is closed under addition and multiplication, but perhaps not inverses. This is the smallest ring in fact, it's a domain. Assuming these elements are all, assuming that K and these elements are all in some big field F that contains K and set X. And I introduced another notation last time. K round bracket A1, A2, AN. Maybe I'll write this a slightly different way. This is the set of all things. Look like this, P1 over such that P and Q are polynomials over K in variables, and I want basically notice what you're doing here. Let me put this another way. A typical element here, right? This is sort of a rational function, and I don't want you to get 0 in the denominator when you plug in your A's, right? Basically, here's what you're doing. You're taking all the stuff in here and taking quotients of it, right? As long as the denominator is not 0, right? This should be the quotient field of this, right? Because everything here is a fraction, something here divided by something here, as long as the denominator is zero. This is the smallest subfield of F containing the field K and A1 N. Now let me give you a concrete example. Actually, let me kind of finish off my thought here. This idea can be extended. If the cardinality that says an infinite set, you'll have infinitely many of these things, and the consequence is now you're taking polynomials out of as many variables as you want, arbitrarily large n, but you only use finitely many things to plug in at a time. If say if this set of elements is a singleton set, then we say that K A is a simple extension. Okay. And finally, if L and M in F are subfields, then the composite LM is smallest subfield of F containing L union M. So this is sometimes this is written this way, the composite field, and what this means is notice that L is contained in F and M is contained in F. So the smallest subfield that contains both L and M is certainly contained in F, but it might be smaller. And so basically what you can do is you can do this kind of thing here. Just take L and adjoin everything in M to it, even if it's an F set. So this is mostly notational. Any questions? Let me give you an example here. Here, let me do this. So let pi, I mean, when I say pi, I mean the real irrational number 3.1411592. If I ever shut up, it'll be rational kind of thing. Now, notice that it's simple. This is the smallest field that contains Q and pi. Now, let me point this out. Actually, there's a whole bunch of stuff in between Q and Q pi. There's a large number. intermediate rings, and this is one of them. Notice this is actually they're both rings. Containment. Can anybody? Oh, you know what? I'm gonna take the easy one here. I know that there's something that's here but not here, right? And I'm gonna call it pi, right? Everybody knows that pi is not right. Can you give me something that is here but not here? 1 over pi. Well, let's check that, right? Let me make sure, right? Now, let me not run my mouth too much. Why is 1 over pi not there?
The bracket part, it's on the polynomial in pi, so pi will not be on the denominator, it would be the rational number on the denominator. So that's why 1 over pi.
That's a very rational argument. That's true, but you need a little bit more. So let's actually go through the steps and see, and maybe you guys can help me out. Let's suppose 1 over pi is in this one. Now she's exactly right. What this means, this is sort of like polynomials, right? So this means that 1 over pi should be with AI rational numbers, correct? Now maybe it's a little bit more. I mean, how do you know that you can't get 1 over pi as some?
Thinking like pi.
Okay.
Something like that.
You know what? I'm a good old boy from Tennessee, parents and cousins and all that sort of thing. So I struggle with fractions. So the first thing I'm going to do is clear that. So actually, I'm going to have to ask you to appeal to something that you may have heard as folklore, but I haven't proved. You probably didn't prove it in algebra 1 either. Does anybody know what the problem with that equation is? Does anybody know what a transcendental number is? Oh, well, maybe we get to explore something. So you have rational numbers.
Just because it's a root of a.
That is correct. So let me take an aside before I finish my thought here. Well, you got your rational numbers. So let's just. Oh, what are we going to restrict to? Well, I mean, you can pretend that this is what I'm talking about, is subsets of the real numbers, the complex numbers, right? So you got your rational numbers, and we're all warm and fuzzy with that, right? It's just quotient of 2 integers. And then everything else is irrational, right? But you can further kind of divide the irrational numbers up into algebraic numbers and the transcendental numbers. Does anybody know how many of you have heard this? Right, maybe you might have heard of transcendental or algebraic numbers, right? So let me give you what this means. To be a member of this exclusive club, you have to be a root of a polynomial with rational coefficients. Notice that this also encapsulates the rational numbers. Every rational number is root 1/2 is root of 2x minus 1, right, et cetera, But you can throw the rational numbers out of this and just look at the algebraic numbers that are not rational. Give me one. root 2, root 3, all complex roots, 3x to the 17 plus 8x to the 5 plus x cubed plus x squared plus 2. Right? All these are algebraic numbers because they're the root of some polynomial with rational coefficients. And then you've got the transcendental numbers, not root of something. Which club is more exclusive? Which club has more members, or are they the same? Let me ask you a question. How many of you know the old analysis thing that accountable union, accountable sets is countable? Right, of y'all familiar with that? Accountable union, accountable sets is countable. How many polynomials are there with rational coefficients? Countable many, right? Because how many polynomials of degree 0 are there with rational coefficients? Countably many. How many of degree 1? Countably many. Of degree 2. To get all of them, take the union of that is countable union of countable sets, right? Each one of these polynomials has finitely many roots. Agreed? So again, you can use that countable union sort of thing. So the number of algebraic numbers is countable. The number of transcendental numbers, say on the real line, uncountable. So if God chose a real number, God is going to choose a transcendental number. So I will frustrate you with that in the following thing. Give me an example of a transcendental number. And I'm going to cheat first by taking pi and e off the table. Give me one that is not pi or e. That's actually kind of a hard question, right? Actually, the easiest way to do it is to do it with decimal expansions. You could do things like put like increasing sequences of zeros in between decimals, and you can build things that way. But there are many numbers, right, like constants that are not known, if they're transcendental or not, right? So this even though most real numbers are transcendental, it's hard to give a concrete example, right? Whereas given our experiences, it's fairly easy to give rational numbers, and once you can give rational numbers, you can give algebraic numbers just by using the rational numbers to build their appropriate polynomial. So given my four-way, what would this mean about pi? If 1 over pi is in there, this would mean that pi is algebraic. And this is a contradiction. There are actually 2 famous proofs that we probably won't have time for here, but if you're dying to know, come by my office and we can kind of talk about it a little bit. But there are 2 famous proofs that pi is transcendental. It is not the root of any polynomial with rational coefficient, and so is e. This contradicts the fact that pi is a transcendental number, and so 1 over pi is not in here. Let me give you another example that sort of contrasts this a little bit. So in particular, before I move on to the next one, this actually shows that this is not a field. Because pi is in there, but its inverse is not. And in fact, this is kind of a look ahead for later. As a ring, this is isomorphic to QX. And the isomorphism is what you might think it is. Just take X to pi, and you will get a 1-to-1 and onto homomorphic QX pi. And this, as you might guess, since this is the quotient field of this, is isomorphic to rational functions in X. But okay, oh, I'm gonna have a more general theorem about this in a moment. Let's look at another example. In fact, now what I'm gonna do is I'm gonna whip out of my magic hat a irrational number that is not transcendental. So oops, got it wrong, didn't I? By the way, there's lots of fields. By the way, I keep going back to this thing here. Can anybody think of another field between Q and Q adjoint with pi? There's actually many fields in between there. But I think one. Oh, thing, because when I write the answer down, you're gonna get angry.
Q of pi square.
Very good. That's exactly right. And see, once I've done that example, you can see there's a lot of things that you can put in between there. Exactly. Right. Notice that this is kind of crazy, right? In fact, here's the thing that will kind of make you a little bit angry. This should anger up the blood a little bit too. These two fields right here, this one is contained inside of this one. Agree? Because if you've got pi here, you've got pi squared. However, these two fields are isomorphic, right? Even though this one is strictly contained inside, there's an isomorphism between them. What about this one? Boy, I can't do the same trick, can I? Because if I try to square this, this is Q adjoint, this is the smallest field containing Q and 2, which is all the way back down here. In fact, I'll go you one step further. In this case, in this particular case, these two are equal. Right? These two very, very far apart. These two equal. By the way, it should be clear to everybody that this is contained in this. Agree? Right? Because this is plugging radical 2 into polynomials, this is plugging it into rational functions. Right? Okay. Let me show you the other way. Let me get the other contained. So to finish off the idea of this example, so for this example, it suffices and this is because as we've observed before, this animal is the quotient field of this. So if this is already a field, there's nowhere else to go. Right. So the quotient field of Q, you already feel is Q, right? Fractions from Q is still rational numbers. Everybody okay? So really our burden is if I can show that in this case, this is a field, then I'm good to go. But we're going to see that it's a field, and we're going to see an important bit of this is we're going to see it is going to depend on the fact that that radical 2 that I've stuck on the Q is actually an algebraic number. It actually is the root of some polynomial. It'll be a little bit subtle where you see it here, but it will develop. Okay. So let well, actually, let's do this. Might work. That is A5. Okay, so a typical element Q adjoined with square root of 2 is just a polynomial with radical 2 plugged in. Everybody okay with it? Now, this is a particularly easy example. We're going to get ones that are a little bit more sophisticated. But can anybody make an observation about how I might compact that form? Well, if you notice what happens is this is rational times radical 2. This thing is rational. So I can group it back with this. The Q will be a rational times a radical 2. So notice that all the even ones, even powers of radical 2 are just rational numbers. And all the odd powers of radical 2 are just radical 2 times a rational number, right? So I can really write this way. Any element Q radical 2 is a form where A and B are rational numbers. Everybody okay? Now, the first thing I claim.
Is that just to be brackets? Square brackets?
I do, yeah. I'm getting really sloppy. Square brackets. Now, let me make a claim here. I claim first A plus B radical 2 equals 0 if and only if A and B are both 0. Right. This direction is pretty obvious because if A and B are both 0, then that's clearly 0. On the other hand, suppose A plus B radical 2 0. This implies radical 2 is minus A of B. Well, let me, before I do this, this means that so B radical 2 is negative A, right? So let me observe now, if B equals 0, then A equals 0 and done. So we suppose B is not 0. Right? In this case, radical 2 is minus A over B, which of course is a rational number, which is a contradiction. Probably everybody's seen that, but is everybody at some point you're passing the proof radical 2 is in fact not rational, right? I'm a fan of that one too, because my favorite proof uses unique factorization. Okay, so now we've got this claim taken care of. Okay, now my next claim is if I have one of these elements Q adjoined with radical 2 that is not 0, then there's also in Q in the brackets right radical 2. Now, already I'm good to go because I know that thing is that fraction makes sense. because that fraction's in the quotient field. I just want to make a stronger claim that no, it's in the quotient field, it's already down in the original ring, right? And I feel like I'm sitting in Sevier County High School's class where some teacher is telling me to rationalize the denominator. Y'all remember that from days gone by? That's what I'm gonna do. I'm gonna rationalize the denominator. What your algebra teacher may not have told you back then is basically you're using an automorphism. You're using a little baby Galois theory to get to the bottom of this. And I'm gonna multiply this by. And let me point out that just to be safe, this claim back here covers this as well. This is not zero, right? Because since this is not zero, either A or B is not zero, which means that's not zero either. But what do I get? Well, I get A squared minus 2B squared. And I know that's not zero because that's a complex number that's a product of two non-zero things. But again, you can check that out. This is again radical 2 business. And this is A minus B radical 2. And this, of course, is A over A squared minus 2B squared plus negative B over A squared minus 2B squared radical 2, which is N. Now, you might look over the various things that we did here and see the magic in this, although it is a little bit subtle in what we did, the fact that radical 2 is a root of a polynomial with rational coefficients is what makes this engine work, right? And it's the reason why Q radical 2 is now equal to this. But whereas we saw for pi, it was very, very different. And so this kind of brings us to a nice point to talk about this notion of algebra definition. By the way, any questions on that rather windy exam? Yes.
So that one, is the first one supposed to be parentheses? Like, because we just proved it's in the parentheses once and then now it's equal to the brackets. Or did we prove it's still in the?
Well, what we proved here, what this claim here proves is this thing is a field. Right.
Okay.
And so since this is field, its quotient field is this, so you have an equality here. Right. Okay, definition. Like K, B, and F, these are fields, of course. And let U be an element of the bigger one. We say that U is algebraic. Over K if U is a root of some. Let me be careful, it's a non-zero polynomial kx, yeah, k dash x. If U is not algebraic, we say it's transcendental. Then U is transcendental. Over. So that's what I mean for an element. It's algebraic if it's algebraic over a field if it's a root of a polynomial, a non-zero polynomial over that field. And if not, it's transcendental. If every element alpha and F is algebraic over K, we say F is an algebraic extension. If there is one, at least one transcendental element, then it's a transcendental extension. If there exists one transcendental element. And of course, by one, I'll clarify one or more. So in other words, one transcendental element sort of spoils the pie, so to speak. One transcendental element in F over K, then F over K transcendental. Let me give you an example. You know, I remember the first time I saw this definition, I thought, wow, you know, algebraic extensions, that means every single thing in that extension is algebraic. Are these things rare, right? I mean, it seems like that most extensions in a certain sense might be a mixed bag, right? In fact, every extension of K has some algebraic elements, guaranteed. Anybody tell me what they are for sure? The elements of K themselves, right? I mean, it's kind of silly, right? But notice that just take U to be in K, right? Which is certainly an F. U is a root of the polynomial X minus U because U is already in K. So every element in the base field, so to speak, is already algebraic. It seems like in general, it ought to be a mixed bag. How hard is it to construct an algebraic extension? We'll see it's actually pretty easy. A lot of extensions are algebraic, but what's in here? Notice that X is algebraic over Q of X squared. Because it's a root of the polynomial T squared minus X squared. Notice T squared minus X squared is irreducible in this field. And you should be jumping on me because I meant the round brackets here. There we go, round brackets. There is no X here to factor this down. This is actually an irreducible polynomial in this field. However, notice that X is a root of this polynomial that's not in here. X is actually algebraic. And in fact, this extension right here is algebraic. But X is transcendental over Q. Let me give you another quick example. One of everybody's favorite extensions of the rationals is the real numbers, right? The real numbers has to be transcendental. Even if you don't know the pioneer transcendental, yes, I know these are numbers. Let me point out that if you look at all possible polynomials with rational coefficients, that's a countable set, which means there can be at most countably many algebraic numbers over Q. And the reals are uncountable. So most of the reals cannot possibly be algebraic. But notice, you might notice real quickly here that the transcendental extensions that I've all given you are in one sense big, right? Yes.
Why is X transcendental over Q?
Well, because X is like it's a variable. So is that it can't itself satisfy. So if not, there exists a polynomial let's say Q0 plus Q1T plus Q2T squared plus QK in QT. Sorry about kind of the change in notation here, because I didn't call that an X, such that plugging in X gives 0, such that X is a root. But if I plug in X to this, I get Q0 plus Q1T. No, I don't. X plus QK XK. And this is not 0 because it's a polynomial of degree K. Right? So yeah, that. So let me give you kind of a first there that kind of feeds into these examples here that I've been talking about. This first one kind of deals with transcendental case. Well, a simple extension. This is theorem 816 16. Let's let K and F be fields. And U and F transcendental over K. So we have two fields. I got somebody up in the big one that's transcendental over the little one. Then KU is isomorphic to KX, where B restricted to K is the identity on K. Now let me go to the trouble proving this one. So this is, I sort of alluded to this a little bit earlier. Here's what this theorem says. If you're a transcendental element, you can't tell the difference between that and just a variable, right? So in other words, if your transcendental element KU, if U is transcendental, it is effectively no different than a polynomial variable, right? So K of U is the same thing as K as rational functions in X over K. Everybody okay with it? And I kind of alluded to this a little bit earlier. So proof. What I want to do here is, like, actually I did this, whatever. Define, I'll just give it a different letter since I'm going in the other direction. Let's say phi from, well, actually, let me first say this. In KX, every element is a form Px over Qx with PQ and Kx. So these are polynomials, and Q of X is not the 0 polynomial. So all I'm saying here is rational functions just look like a quotient of two polynomials, P of X over Q of X, and I just want the Q of X to be a non-zero polynomial. I am going to define a homomorphism okay. Remember, we're in math class, so it better be easy. Any ideas? What's the most natural thing I can do? That's right. Just blindly plug in U over here. Right, so. Now. There should be alarm bells that go off. What's something that you should immediately worry about?
Is Q of U is 0. It's not possible.
It is not possible, right? Note. Q of U is not equal to 0, because U is transcendental. And send over K. Because if Q of U was 0, that would mean that Q would be a polynomial with coefficients of K, and U is root of it. This can't happen, right? But okay with that? So this is a well-defined function that goes, capital Phi goes from rational functions in X to quotients of things in, quotients of things in K square bracket U, where the denominator is not 0. Notice that well, I mean, this is just really rewriting fractions. Q1, Q2, I'll suppress the X, my apologies. There's P1, Q2, plus P2, Q1, and then plug in. So this is P1U, Q2U, plus P2U, Q1U, Q1U, Q2U, which is P1U, Q1U, plus U over Q2U, which is there we go. And also I'll let you verify that this is actually easier. This is also true as well. So what do we have? We have well-defined homomorphism. Let's see, we need one-to-one and onto. To kind of finish off this, we need one-to-one and onto. Let P of X over Q of X be a kernel of this animal. So this means that PU over QU equals 0. We can plot PU is equal to 0, and this is a contradiction. Well, let me not say it. So P of X must be 0 polynomial. Because the only way for this fraction to be 0 is for the numerator to be 0. The numerator 0 means that U is a root of that polynomial. The only, since U is transcendental, the only polynomial it can be a root of is the 0 polynomial. So P of X over Q of X is 0. Is 1, and this is onto. By definition, because by definition it is just plugging in quotients of polynomials. Also notice that if you take B restricted to K, is the idea. Because write your K as just K over 1, and when you plug in it and do anything, it's the identity. Okay. Any questions on that? Okay, that's the first little bit with transcendental. We will get to algebraic next time. I'll give you a neat theorem that kind of ties up some of these examples that we did today. Any questions? Any questions? Oh, our award-winning researcher in the school this year, Eva Murphy, is going to give a talk basically on her research and also about some experiences in grad school. You guys are already living the grad school experience, that is true, but it's good research and I would highly recommend it. So think about coming Friday and we will see you all next time.